Okay, so we will continue with analysis of Brownian motion. Yesterday we looked at measurement of particle diffusivity, and then we also derived an expression or an equation which is what is called as Stokes-Einstein relation. That will help you to calculate what is the dimension of the particle if you know the diffusivity, right. That is what we had done, and in that connection we had just started with what is called as a dynamic light scattering. So, I just want to clarify a few things. So, I had mentioned that the scattering of light typically comes about if you have any localized non uniformities or heterogeneities in the sample. Okay. And light scattering is a consequence, okay, of interaction of photons, right, because whenever you take any light source, it is made up of photons, right, and interaction of the photons that make up the light with the electronic structure of the atoms or the molecules that make up the particle, okay, or the dispersed phase is what gives rise to what is called as light scattering. Okay. And whenever people do light scattering measurements, what they do is they measure what is called as scattered light intensity. Okay. And the way it is measured is they will have a instrument which can measure radiation, right, and typically photons. Okay. And these photons, again it depends on the kind of radiation measurement device that you are using. Typically people use a PMT, what is called a photo multiplier tube, okay, in which what is done is you basically collect the number of photons that fall onto the device that you are using, and typically the measurement of photon or the intensity is expressed in something called as a KCPS, kilocycles per second. Okay. And depending upon the kind of a scattering unit that you have, okay, this the photon count that you measure, it varies. Okay. In general, one thing that you should know is that any scattered intensity, okay, I, that is detected by any device that one is using, it is actually proportional to volume of the particle that you have in the dispersion to the power 2. If Vp is the volume of the particle that you have in the dispersion, the scattered intensity goes as volume of the particle to the power 2. That means larger particles will scatter more light, okay, or the intensity of the light that is scattered by a larger particle is higher compared to the intensity of the light that is scattered by a smaller particle. Okay. Then as I mentioned, people can use white light, laser source, or X-rays or neutrons for scattering, right, as a light source. And as I mentioned, when one uses white light, okay, what is exploited is the difference in the refractive index between the particle and the medium is what is exploited. If X-rays are used, okay, the scattering actually comes because of the interaction of X-rays with the electron clouds, that the atoms and the molecules will have. And if you have neutrons as a source of radiation, then the scattering occurs because of the interaction of the neutrons with the nucleus of the atoms or the magnetic moments of the atoms of the molecules that constitute the particles, right. So, that is a difference, but except for the origin of scattering, the way the data is analyzed, okay, the way the scattered intensity is analyzed from any of these experiments where you use light, X-ray or neutron, the analysis is very similar, okay, but only thing is the scattering originates from different reasons. Okay. I had mentioned this. So, we typically people do two kinds of scattering experiments, what is called as a a static light scattering, okay, in which what is basically measured is you have a sample, you have a detector, and then you go on accumulating intensity as a function of time, and then what you get out of the measurement is a time average intensity, okay, time average scattered intensity. Okay, there is a term here, is called a scattering vector. Okay. So, that scattering vector actually is defined something like this. It's typically people use either Q or S. It goes as 4 pi, okay, divided by lambda, where lambda is the wavelength of the radiation source that you are using, multiplied by sine theta by 2, where theta is the angle at which you are collecting the radiation, the scattered intensity. Okay. Okay, so, in static light scattering, what is measured? The time average intensity is what is measured. In dynamic light scattering, what are measured are the fluctuations, okay, in the light intensity as a function of time. Okay, that is what is measured, and typically whenever people do static light scattering, there is a radiation source, there is a sample, okay, and you collect scattered intensity across many detectors. Okay. That means, I am basically collecting scattered intensity at different theta, right. Okay, that is what is typically. So, what you get from the static it is I of q, okay, that is q here, okay, as a function of q is what you get from static light scattering experiments. You are measuring the scattered intensity as a function of this scattering vector, okay, that is the data that you get, and you analyze that data to get any meaningful quantity that you want to get out of your experiment. Okay. And in the dynamic light scattering measurements, what is measured is a fluctuations in the light intensity. What you are measuring is your I of t, okay, that is you are measuring scattered intensity as a function of time. Okay, that is the difference between the static light scattering and the dynamic light scattering. Okay. So, this S I already defined, right, it goes as 4 pi by lambda into sine theta by 2. Okay. So, now depending upon the wavelength of the light source, okay, depending upon the wavelength of the light source, the range of S that I have access to will vary. Okay. If lambda is more, okay, your Q, right, or S is going to be smaller, right. If the lambda is small, your Q is going to be larger. Okay. You should think about Q, okay. So, inverse of Q, okay, you see the Q will have a unit of nanometer inverse, therefore, inverse of Q will have units of some length scale. So, therefore, what you are changing, okay, what you are doing by changing the wavelength is that I am basically able to access different length scale by using different radiation length source, and that length scale that you have access to, okay, if we call it as some length scale L, is proportional to 1 over Q inverse, okay, or 1 over S inverse, 1 over S, right. Now, therefore, if you use X-rays and neutrons, okay, which have a lower wavelength, then they can help us probe structures at much shorter length scale. Okay, I am able to go to much smaller and smaller length scale, and I am able to access microstructural information at a very small length scale compared to what you would do if you use laser or visible light. Okay. Yeah, so typical light scattering experiments. So, this is for the case of static light scattering, as I mentioned earlier. So, there is a beam of light, in this case X-ray wavelength lambda, okay, and there is a sample, and I had mentioned that typically these the sample and the detector are actually kept in a vacuum environment. You don't want light to scatter off from whatever medium in which it is. Typically, as I said, you can get okay. So, in this case the detector is what is called a two-dimensional detector, okay, because it's basically a screen. Okay, you should think about there's a sample, there's an X-ray beam, and something is scattered, and it falls onto a beam. Okay, and then this q is again 4 pi by lambda into sine theta by 2. Okay, that's a scattering vector, and typically what is done is there's actually something called a beam stop. The role of the beam stop is the intensity that is in the center will be very high. Okay, if you don't have beam stop, it could damage your screen itself. Therefore, typically you put some carbon source or some stuff which really absorbs. It doesn't cause some kind of damage to the, and it also acts as a reference, right? Because when you're changing theta, okay, theta in the center is going to be 0, right? Okay, because your incident beam and the scattered beam, the angle between them at that particular location would be 0. And therefore, if you go outward, okay, what is changing is theta, and in turn what is changing is your q. Okay, so typically, one gets patterns like this, and these patterns will have information about the structure, okay, that is inherent to the sample that you are working with. Okay, in this case there is a chain of particles, and if you have a chain, okay, you will typically get a pattern which looks something like this. Okay, and what people do is you can go back and read up a little bit about it. So, what people do is they do what is called a radial averaging. Okay, what I can do is I can, of course, this pattern is not very symmetric, right? But if you have a pattern which is very symmetric, what I can do is I can do what is called a radial averaging. So, if I go from here to this direction, and what I do is I rotate that. Basically, I am taking a particular line where I am basically changing the radius, right? Okay, from the center, which in turn I am basically changing q, right? And if I average it across many lines like that, like many lines, okay, or all the lines that I could draw, then I get average intensity as a function of q. Okay, so basically from the 2D patterns you do radial averaging to get one dimensional scattering intensity patterns. So, therefore, your data would look something, okay, I have q may as a function of q may look something like that. It depends on your sample again. Okay, maybe at some point I will show you some data from a particular sample which has some well defined particles of some sizes. And I had mentioned that what you are doing, you can think about scattering as imaging in a Fourier space, okay, or what is called as a reciprocal space. Okay, this is an example. So, that is a microscopy image. If I were to do Fourier transform, your patterns would look like this. That means, if I have any sample which has arrangement like this, like what is shown here, then your scattering pattern, if you do experiment, your scattering pattern would look something like this. Okay. Okay, so before we move on further, so this is again will tell you something about the typical sizes that one can measure by using scattering experiments. So, if you look at SLS, the static light scattering, what is measured is the angle dependence of the scattered light, okay, and typically you can measure anything of size larger than about 50 angstrom, that means about 5 nanometer and above, okay, is what you can measure with SLS. Okay. And there are instruments where I can measure by using SLS principles, you can measure things up to a few millimeters as well. Okay. Okay, it really gives you a very large size window that you can measure with this technique. DLS, what is measured is time or frequency dependence of the scattered light, and typical size range one could measure. There are instruments where you can go to as low as a nanometer, okay, and typically
In DLS, so the wave vector is constant.
So okay, yeah. So I'll come back when I talk about DLS. I'll mention this point. So his question is, in DLS is the wave vector constant? Okay, so we'll come back to that. Okay, and of course there's something called as S stands for small angle X-ray scattering. Okay, and small angle neutron scattering. Okay, these experiments are similar to SLS, but you are using X-ray and neutron as a source, and typical length scale that I can have access to is about 0.5 nanometers, or depends on the wavelength of the X-ray one could generate, but you can look at sizes of this order. Okay, so now now we'll move on to DLS. Okay. I said this is a commercially available example of a commercially available instrument. I had mentioned you can use it for measuring size of the particles, polymers, surfactant structures. People also use this for measuring charge on the particle. Also it gives you a way of measuring molecular weight as well. Typical, if you open the instrument, right, so typically this is what it will have. Essential components would be laser, okay, which basically will give you radiation of a particular monochromatic, right, of a particular wavelength, and there is a set of lenses basically to get a collimated beam, and there is a sample. Okay, so this what is shown here are two beakers, right? There is one beaker here and there is a small beaker there. Okay, and the reason why not every instrument will have this kind of a setup, the reason why it is done is that when you have a beam coming in, it is coming typically in air, right, and then it is going to go into a sample. Okay. Now when that happens, there is going to be a change in the refractive index, right. You do not want any of that happening. So what is done is you take your sample and you put this sample, say that this sample is in a glass cuvette, okay, and you immerse that sample in a container which has a fluid whose refractive index is same as that of the glass. Okay, therefore, it will essentially avoid some scattering effect that may come from the cuvette itself. Okay, change the refractive index. So, but if you don't use glass cuvettes these days, you have a plastic cuvettes which can be used without this without this bath of fluid. Okay. Okay, and typically you will have a PMT or some kind of a device where you can measure the photons that are that are scattered from the sample, and this theta, right, and as you can see here, right, so these photons are collected at a fixed location. Okay. Typically if you go back and look up instruments, there are instruments where this theta you can collect it at 90 degree. Okay. You can collect at something like 135 degree somewhere here, or you can also collect at some 15 degrees. So, it depends on the instrument specifications. Of course, there are instruments where I have access to changing the length as well. Okay. In such a case, I can vary it across a large range of theta, and I can do both DLS and SLS with the same instrument, because if I basically if I can do DLS measurements at every theta, that is as good as doing a SLS measurements, right. There are instruments like that, but a lot of tabletop instruments typically work at fixed theta. That means your Q is fixed. Okay. Therefore, your scattered intensity that you are collecting is always done at a fixed Q. Yeah. And I mentioned something about scattering volume, the interaction of the light beam and the incident beam and the scattered beam will give you what is called as a scattering volume, and unlike microscopy based technique, this scattering volume will have a large number of samples. Therefore, you get a better average, okay, of the size of the particle that you have. I have mentioned this already. it can be measured, you can measure the size of the particles, micelles, vesicles, polymers, name it. Okay. The only thing is there should be a enough refractive index difference, okay, between the dispersed phase and the continuous phase, right. Again, size range, I had mentioned that you can measure sizes as long as particles exhibit Brownian motion, okay. And what is measured is a fluctuations in the scattered intensity as a function of time. It will look something like this, okay. This is your intensity, okay. S is same as Q, okay, but of course Q is fixed here. So, either I can call it as IFT itself, because your Q is fixed for in the case of DLS measurements, and that is measured as a function of time. Okay, these are the fluctuations that you have. Okay, that is how it varies. It varies around a mean value. Okay. Now, okay, why are we interested in the scattered intensity as a function of time? Because the variation of scattered intensity with time contains information on the random motion of the particles. Okay. The intensity fluctuation that you saw here, that arises because the particles are not fixed in space. If you somehow fix them in space, okay, then what will happen is your intensity is going to be a constant. But the fact that the particles are continuously moving around is what gives rise to this fluctuation in the intensity. Okay. And this can be used for measuring the diffusion coefficient, and once the diffusion coefficient is known, I can actually get what is the size of the particle, right. And typically size of the particles are measured by something called as Stokes-Einstein relation. This is applicable if you have monodisperse particles, this particular expression, right, because the particles are of same size, okay. And of course, it is if the particles are spherical, and one has to ensure that you work with dilute solutions. Okay. This is one of the important requirements whenever you do DLS measurements. Okay. So, what do I mean by dilute solutions is where the interparticle spacing, okay, interparticle spacing is very large. That means there are no particle-particle interactions. Okay, that is one reason why you should be working with dilute dispersion. The second reason why you should be working with dilute dispersions is also because if you have too many particles, okay, if you have too many particles, what will happen is your incident beam, it is diffracted or it is deviated when it hits a particular particle, and before it comes to the detector, it may hit many other and come out. Okay. There could be what is called as multiple scattering events. Okay. When you have multiple scattering events, okay, you cannot apply the analysis that we are going to do, for such, the typical analysis that is applicable for monodisperse, dilute dispersions. Okay. That is because, as I said, the scattered intensity, we are assuming that whatever is scattered is because of a single particle motion alone. Okay. And if you have too many particles close by, the other particles could also influence this fluctuation. Okay. And what is typically measured in DLS is what is called a hydrodynamic radius, okay, which is the size of the particle in the solution. Okay. What I mean by that is that so if I were to take some particles dispersed in a fluid, okay, and say that I have taken a same particles, okay, a small drop of it, and I have dried these particles. Now, the particles are on a substrate. Okay. Now, I do some microscopy. Okay. So, in this case I get the size of the particles in the dry form, and in the second case if I do DLS measurements, I get the size of the particles in solution. It turns out that typically the size that you measure with the DLS measurements is always slightly larger than the size of the particle that you measure in the dry form. Okay? And the reason is because you could have a particle that could have some charges on the surface. The effective size of the particle may be slightly larger because you have charges, okay, depending upon like say the surface charge density, depending upon the arrangement of water molecules around the particle surface. Typically you may measure sizes that is slightly more larger than what you would measure with the dry technique. Okay, so the sizes that you measure with DLS is what is called as a hydrodynamic size. Again, I have taken this example from this source. What you are looking at is a schematic of cases where you have these are all water molecules, right? These are all water molecules, okay, and they are essentially bombarding the particle, right? This is a large particle, this is a small particle. What can you say about these two?
Small particle has more Brownian motion.
Small particle has more Brownian motion, okay, which is reflected by the fluctuations are too many, right? Okay, and that is little here. Of course, what is not apparent in this is that I said that your scatter intensity goes as volume of the particle square, right? Therefore, if I were to look at the average value of the intensity, this will be much larger for this compared to what you would see for this, right? So, these are some. So, when you do your experiments, you can you can look for all these things, so that you will get an idea as to whether what I am measuring is something reasonable or not. Yeah. Okay. So, now okay, that is what you measure. So, there are instruments where you can actually access this information. Okay, if you take a commercially available instrument, a DLS instrument, there are instruments where they display this scatter intensity as a function of time, but many instruments do not. Okay, but what they show when you use any particular instrument is look something like this. Okay. This is actually obtained from that scatter intensity measures a function of time, okay, that is g1 of tau, okay. Because I know how I of t varies as a function of time, I can guess this quantity, right. This is intensity at a particular time, intensity at a particular time plus some delay, okay, and intensity at a particular time, right. I have access to all this information. I can calculate g2 of tau, and this is what is called the instrument constant. So, what I am trying to say is that the scatter intensity as a function of time is reported as what is called as a electric field auto correlation function, okay, which is derived from the fluctuation in the intensity that you measure. Okay. Now, this function, okay, you can fit that to a exponential function, okay, and from that exponential function I can get minus d time q square, right. You have g1 of tau as a function of tau is what you measure, and you should look for this number, okay. This is tau is in microsecond, depending upon the length scale of the particles that you have as a dispersed phase. Your this unit would vary. Okay, if you have very large particles, then you will see that this decay, right, it happens somewhere towards a larger tau. If you have very small particles, it will happen to the decay, right, it will decay at a lower tau. Okay. Therefore, one could actually look at where does it decay to 0 and then already kind of infer about what is the size of the particle that you have in the dispersed phase. Okay. So, now from the exponential fit I can actually get what is minus d times q square. I know q square because I am doing experiments at a fixed q, and I get this, and from that I can actually get what is the size of the particle. Okay, that is what is typically done. So, this is some data where we were trying to look at these are example of what is called the emulsion fuels. Okay, these have very tiny water droplets in diesel. Okay, the work done in our lab with Preetika and Nikit. Okay, and what is being measured is that whenever you have an emulsion fuel, right, you would want the fuel to be stable, right, for a long period of time. So, we were trying to look at what happens to the fuel if you store them for a long period, 6 months, right, and this is the autocorrelation function measured as a function of decay time. And one thing to notice is that all of them overlap, right, almost lie on top of each other. That means if I were to extract size of the particles from this experiment, I would expect the size to remain the same, right, and that is what you actually see, okay, which is done by a simple exponential fit. Okay, I get d times q square. Okay, I know what is q, and from that I get d, okay, and then use Stokes Einstein and get the size. Okay. So, you can do analysis like this. Okay. But it is not necessary that you should always have, you will have monodispersed particles, right. So, if you do not have monodispersed particles, what you do is instead of expressing g1 of tau as a single exponent, you basically express that as a sum of exponents. Okay. Okay, it's you can express them as, depending upon if you have bidispersed particles, then I can say that it will be sum of 2 exponential functions. If you have tridispersed, I could use 3 exponential functions. So, therefore, in general, if you have a size distribution, then I can express g1 of tau as summation of many exponential functions. And if you have something like that, then what you do is you can expand an exponential function around some average tau bar. Okay, this tau bar is what is called as a decay constant. Okay, it is what is called as is the decay constant. And then if you kind of leave out all the higher order terms. Okay, so you what you do is if you plot ln of g1 of tau versus tau is what you have access to, right, then I can fit a function and I can get what is tau bar and what is mu by 2. Okay. And from tau bar, if it is tau bar, I can get d effective, that is the effective diffusion coefficient, not d anymore because you have particles of many different sizes, and because I am interested to get what is the average size, I will get what is d effective. Okay. And this mu will have information about the polydispersity of the sample. Okay. These are again some experiments where we were trying to measure again some size as a function of time for a different kind of emulsions, where as a function of time you see that this is as a function of time. Okay. This variation already tells you that there is something changing, right. There is a change in the size as you wait for many days, okay, and that is the data that you obtain. Okay. For the first sample, that is the size, okay. Second sample, that is the size, right, and for the last sample, that is the size, and I can extract what is called a polydispersity index. Okay. So therefore, you can work with either monodispersed samples or polydispersed sample. You can extract the size or the polydispersity index from such measurements. I have a couple of more examples. This is using light scattering to measure what is called a CMC, right, critical micellar concentration, right. So typically what happens is, if I have, like say for example water, and I add surfactant molecules, right, which are represented something like this, that is the head group or the hydrophilic part, and that is the tail group or the hydrophobic part. The moment I put them in water, initially at low concentration you will have individual surfactant molecules, and then some of them may go to the interface because of the surface active nature, and then with increase in the concentration you will reach a condition where the interface is completely populated with surfactant, and when you add more surfactant, that is when you get these micelles, right, and that concentration is what is called as a critical micellar concentration, right. What you are measuring here is the intensity I mentioned, right. It is intensity is in kCps, and on the right side you have hydrodynamic size. Okay. I mentioned that if you look at because intensity, I said intensity is proportional to volume square, right. Initially you have only monomers, right, or small aggregates, you do not have any scattering or very little scattering, but at a particular location you see that the scattering basically increases, right. That you can think about, this could be because of the change in the size from maybe a small aggregates to a micelle, right. So therefore that point you could think about as a CMC. Okay. The other way of looking at this would be that, of course, when you do use DLS measurements below a particular concentration, again you have small species, your sizes are going to be very small, okay, maybe below the detection limit of the instrument itself, but at a particular concentration you see that you get a size, a significant size which can be measured with with reasonable accuracy with these instruments, okay, and that is where essentially, so you can see that the whatever whether I look at the intensity at a particular concentration or the size, both of them coincide, right. Okay, that you can think about as a CMC. This is another experiment where they were looking at a dispersion which have what is called a VTP, volume phase transition, and that volume phase transition happens. What do I mean by volume phase transition? You have a particle, it is an example of what is called as microgel particles. Okay. And these microgel particles, you should think about them as, there is a center where there is a high cross-linking density, these are polymeric particles, however with a center where the polymers are highly cross-linked, and a outer region where there is the cross-linking density is less. Okay. Such particles, a particular class of such particles called PNIPAM, polynipam, okay, which stands for something like this. Okay. These particles, if you put them in water and if you heat them up, okay, if you subject them to temperature change, they have a transition going from a expanded state to more like a collapsed state. Okay. So what is done here is measurement of size as a function of temperature, okay, and at some, so this is as you decrease the size, so as you increase the temperature, there is a decrease in the size, right. You can do measurements like that to infer about volume phase transitions in dispersions like this. Okay. So, now the last part that I wanted to look at is analysis of sol-gel transition in materials by probing motion of colloidal particles. Okay. I have taken an example here just to give you what is sol-gel transition. This is an example where you have oppositely charged particle mixtures. You could think about this as positively charged, negatively charged particles, and you mix them. Okay. And this number that you see here, it tells you the mixing fraction. Okay. So, 0 means it is completely one type of particle, 1 means it is completely other type of particle, 50.5 means both of them are in equal proportion. Okay. Now, I want to ask you a question as to, of course, they look very different, right? To visually they look very different. If I want to ask you, is there a sol-gel transition, okay, in these samples? If I want to do that, what will you do? So, we understand what is sol-gel, right? In sol, you have particles. In the gel, the particles form a network, right? I had mentioned that is solid like, right. There is a space spanning network of the particle, right. One of the simplest way of doing this would be just invert the vials, right. Very simple, you just invert the vials. Okay, you see that liquid here, it just flows. There is, in this case, there is some a solid and some is fluid, but however at some concentration everything remains, right. So, right now if you want to infer sol-gel transition in materials, what people do is they use a technique called microrheology. Okay, in which what you do is, in the system that is undergoing gelation, you put in some probe particles. Okay. These probe particles, if you are using microscopy, typically you take particles which are micron size length scale. So, in this case they have taken polystyrene microspheres of 1.05 plus or minus 0.01 micrometer dimension. You put these probe particles in a solution which is undergoing gelation. Okay. And then the only thing that you should ensure is that the concentration of these particles is very low, and these particles in no way should influence the gelation process, right. And what you do is you look at these probe particles and you measure their Brownian motion. I can get mean square displacement, okay, as a function of time. Okay. We have discussed how to do that, right. And what you are looking at is two separate systems. Okay. In one case it is a peptide, in other case it is a polymer. Okay. And what is being measured is mean square displacement as a function of time, and we learnt that your mean square displacement, okay, will actually go as t. That means your prefactor, okay, will have a slope of 1 if the particles are in a viscous fluid. They are purely diffusive, right. They are in a viscous fluid. However, when the gelation happens, your del square of r of tau should almost become 0, because the particles are stuck in a network, okay, and they do not exhibit any Brownian motion anymore. Okay, that is what you see here, right. If you look at this case, what they had done is they had added a reagent which will induce gelation. Okay, when there is nothing, the slope of this mean square displacement as a function of time is 1, but with increase in the concentration it's almost flat. Okay, therefore, just by measuring mean square displacement as a function of time, I can infer something about sol-gel transition. Okay. People also use these kind of probes to look at what is called as a structural heterogeneity. Okay, again I am going to take this example of gels, right. So, if I have a colloidal gel, now when I say colloidal gel, so this is, say that this is a particle network. Okay. So, now if you look at a colloidal gel, so it will have, say that I have taken a dispersion which has say 50% particles by volume, and I have made that to gel. Okay, I have induced gelation. So, you will have 50% is still water, right, or the fluid, the continuous phase, okay, whatever that you had, it is still 50%. Now, if I have a probe particle, then depending upon the whether a probe particle is in that free space, okay, or whether it is embedded in the network, okay, it will either exhibit this random motion or it does not, right, depending upon, okay, whether it is in the part of the network or whether it is in the pores, okay, or the fluid between in the network. Okay. Therefore, by doing some experiment like that, I can actually look at what is the structural heterogeneity. Okay. So, therefore, measurement of Brownian motion is a very powerful tool. You could use it for studying particle size. You can do experiment like this where I can infer something about gelation time or the dynamics leading to gelation and things like that. Okay. So, maybe with that I will stop here.